He was a part of the NASA's portfolio. That's why he's been introduction, Mark sir. So I'm Kailash Kalidoss. I'm a first lieutenant in Civil Air Patrol. I represent Squadron 80, and I also represent the Group 2 as a whole as a AEO. I'm also a NASA Solar System Ambassador, so that's how I got to know about several things, including the James Webb Telescope, through the web team that I interact with at NASA. So let's begin. So who is James Webb? So who was James Webb? James Webb, many people will not know him outside the US that well, but just to highlight, he was a big contributor for space science, and he was a part of the NASA's portfolio. That's why he's been named after this telescope. So he was the second administrator of NASA, starting from 1961 to 1968. He oversaw the first manned spaceflight program, which is Mercury, and the second one too, which is Gemini. He also oversaw Mariner and Pioneer planetary exploration programs. He oversaw the significant Apollo program. And then he insisted that NASA should have a strong science program going forward. So that given the reputation of the man, I think NASA has rightly chosen his name for the telescope. So moving on. So this image here is the Hubble Telescope. So the 20th century of astronomy tackled many questions through the Hubble. So Hubble provided us path-breaking images, but what it did not do is we did not get answers in pursuit of objects that are several light years away. For example, the Hubble did not give a lot of answers about our first galaxies and our first solar system objects and the other objects that are in our universe that actually began when the Big Bang actually occurred. So we are not discounting anything. Hubble has still given us tremendous scientific return and often stunning beauty in its pictures, but we have to move on to a better telescope to discover the origins of our universe. So hence the Webb comes into play. So this one here is an image captured by Hubble. This is what Hubble saw. It's not a black void, but it's a rich field consisting of thousands of galaxies. Most importantly, though, none of these galaxies seen by Hubble were primordial, which means none of these were the first galaxies. So astronomers recognized that to continue this case, we had to pursue a different vehicle. So that's one of the cases that drove to the development of the Webb telescope. So I'm going to briefly touch upon a concept called Redshift. So Redshift is nothing but shifting towards the larger wavelength in the electromagnetic spectrum. So I'm not going to go more into it, but for the purpose of this presentation, I'm going to say the more the redshift, the greater you can see. In terms of time. So you can go into more light years, more the redshift. So that's all the correlation is. So for example, a redshift of 3 corresponds to 2 million light years, and redshift of 10 corresponds to 500 million light years. Million years, sorry. So let's move on to the next slide. So this is the Hubble, and side by side you also have the Webb, comparison of the two. So comparison of some important characteristics of Hubble and Webb, it's actually coming up on the screen. It's playing now. Sorry, I have to go back. There you go. So the primary diameter, if you see, the ability of the telescope to see faraway objects is dependent on the primary optics. So if you see the Webb telescope, the primary diameter of the mirrors is 6.5 meters. And it's lighter than the Hubble, but at the same time, the most important thing about Webb is that we are operating at a very, very low temperature. If you see that 223 degrees centigrade there, Celsius there, is because we are seeing things in the infrared region. So we need a lot of temperature, sensitive instruments to be put on board. So we don't need any interference from our sun or any other object that's going to spoil the observation that we're going to do. And if you see, the other important thing is the orbit. So the Hubble is in the lower Earth orbit. It's around 550 kilometers away. But this is going to be far more deeper into space. So we're going to place this in an orbit called L2, which is 1.5 kilometers away. So L2 is nothing but Lagrange point 2. So I will explain what is Lagrange point later. But that's what it is like. It's going to be deep into space, and we are trying to launch this by December. So December 20th is the next date I heard, but it's a moving target because there are certain challenges that NASA is experiencing. Hopefully, it will not get more delayed. I think this is the last date on the date. So it's going to be at least going to last for 5 to 10 years, and it's going to be launched in a European launch vehicle called Ariane 5. So I have some trouble playing this. Okay, got it. Okay, so I talked about the optical element OTE, which is consisting of the primary mirror, secondary mirror, and the backplane. The reason we have the backplane is to actually avoid all the sun's interference, the rays and the heat that are generated by the sun. You don't want to see anything on the other side of the telescope. So basically, it's a filter. And then you have the spacecraft element. You have the sun shield. You have the communication buses. And then the individual modules that are responsible for capturing images in different wavelengths. So basically, you have an infrared and a visible spectrometer. And then Webb required most missions in the area of technology in order to reach its science objectives. So we'll introduce those technologies when they're needed. And then the science goals is typically what we are really concerned with. So I will cover them in the next slides. So we'll start with the instruments and move outward. So the previous animation, I've just showed you what are the most important characteristics of the mirrors and so on. So we are concerned with wavelengths in the near infrared, mid infrared, and wavefront sensing and control mechanism that actually triggers which wavelength which you are interested in, depending on the object. Apart from that, we have micro shutters. We have a cooling mechanism just to keep the temperature really low so that we can observe IR better. We have a backplane, lightweight cryogenic mirrors. They are made up of gold. For infrared, they tend to work better. And then they are not one single structure. They are actually made up of several hexagonal structures put together. And then you have a sun shield coating. That's very important to not leave any radiation from the sun impacting what we observe on the telescope. Moving on. So this is the near IR specification. So basically, they are putting together the near IR module here on the telescope. That's what this picture shows. And this is a big team working on these instruments. There are many instruments that are going on board. Then there's the mirror. As I told you, it's 6 to 8 meters class, segmented cryogenic mirror, diffraction limited at 2 microns. So it's coated with a very thin layer, about 1,000 atoms thick of gold, because it is considered the best reflector of infrared. How is it done? Like, gold is vaporized in a vacuum chamber and deposits of a thin layer on top of the mirror segment. Are you able to hear me at this point?
Yeah,
yes,
we hear
we
you.
hear you.
Oh, okay, okay. So I
Yeah,
thought like there was a connection loss or something. Okay, thank you for that. So that's why we use gold. We also use amorphous glass to protect it from scratches. Each segment reduced in a lightweight process from 270 kilograms to 20 kilograms. So the polishing of the mirrors are done so carefully so that when the primary mirror is enlarged to its size. So basically we use in the launch vehicle, you cannot put a mirror of that size in it. So we use origami techniques to actually um, collapse it into a much more smaller size. And it actually opens out in space later. So that's one of the things about fascinating things about Webb is that the whole telescope is within the payload, but it's kind of very shrunk when in its in its launch stage, but it's going to like open out in space. So the mirrors are polished so carefully that the primary mirror was enlarged to the size of continental United States at its highest point, would be only 5 centimeters tall. Then we are talking about cryo structures. Cryogenic, thermally stable telescope structures are much smaller than the James Webb were produced for other missions. But this is one mission where we take it to the next level. So prior to the James Webb, there were no thermally stable cryogenic large-scale composite structures produced. So the reason I said was like to view in the IR range, it's very important that we go into temperatures that are very low, and that's why we need cryo structures to support the entire operation. So the thermal stability requirements again are more stringent in James Webb because this is the first mission to utilize a primary mirror riding on a black plane. So sun shield technology is another important thing which we have to give a consideration. So the greatest challenge here is proved to be not the material but the complex deployment system. So how are we going to deploy it in space? So basically the origami comes into play there. If you see the picture on your top right, so several layers are actually squeezed in, and then it opens out in a very careful manner when after launch and it's been put into its orbit. So the whole telescope is going to actually be comparable to a tennis court in size. So again, the most important thing here is we are having a temperature reduction from the hot side to the cold side. So if you consider it like a fairness cream which has an SPF, sun protection factor, then the SPF of James Webb will be 1 million. So it's very, very high. So some things about the spacecraft now. The spacecraft element testing finished in May 2019. After that, it was integrated with the telescope to form the entire James Webb Space Telescope. So we have the spacecraft bus combined with sunshield to make up the spacecraft element. So that's on the image on your right. And it was developed by Northrop Grumman. So let's talk something about the launch. So the Webb is set to launch on top of ESA, the European Space Agency. So NASA is working with the ESA and several other space agencies for this mission because it's very, very large in scale. So it's going to launch on an Ariane 5 it says March 2001 to 2021, but it's going to be in December thanks to the delays in the project. So it's going to be from French Guyana. So it's going to make a 1.5 million kilometer journey to its destination at the second Lagrange point. So I'll talk about Lagrange point in the next slide. So Ariane 5, to give a background, it's one of the most successful launch vehicle in its class with a number of successful launches. So the launch is going to happen from South America, French Guyana, near Kourou. So this is an animation regarding the L2. So if you see, L2 is nothing but point where the gravity of all gravity acting upon the telescope is actually nullified. So you have the gravity system through the moon, the earth, and the sun. So L2 is a point where gravity from all of these are equal so that it stays in orbit. So you can learn more from it from the link here. So that was the entire cycle of the video, from launch to it being put into L2. So let's talk about applications, web in the world. So first thing is about the wave front sensing technology. It was developed accurately to measure the shape of the web mirrors. So this is called spin out. So we see what technologies we actually use in our real world from the web research and whatever came out of the web. So eye doctors now use the sensor for fast eye mapping diagnosis of ocular devices, and potentially it has improved surgeries as well. So the technology from web is actually spinning out and providing us with so many other things apart from what it's doing from space. Then we have the laser interferometers. So these are high-speed test devices that were developed that use pulse lasers to freeze out vibration effects for nanometer precisions. So this is a technology that now generates a lot of revenue from the aerospace, astronomy, semiconductor, and medical industries. And then the tech applications side for restoring Hubble. So web investments in cryogenic applications. Specific integrated circuits made these specialized small circuits programmable. So these are now actually put into Hubble as well. So they are while conducting repairs. So we now have an advanced camera for surveys now in Hubble. So developing the web also helped the Hubble in some way. And then we have astronomical detectors. So for advanced near infrared detectors, that is one of the primary instruments of the web. The universal choice was for astronomical observations in space and the ground. But the technology is also now used in earth science and national security missions. So the purpose of the slide is to actually say that this technology is not just limited to study our universe. So whatever technology spins out, it's going to be useful to mankind in a different way as well. The next slide is a little about who's behind the web. So we have over 100 American, European, and Canadian universities, organizations, companies across 14 countries, and spread over 29 US states who are somewhere responsible for the web project. So within NASA, you have the Goddard Space Flight Center, which manages the project and the micro shutters. JPL, or the organization that I volunteer for as a NASA Solar System Ambassador, that is doing mid-infrared instruments. So the Ames Research Center here in Silicon Valley, that's right in our territory. So it's doing the detector technology. The Johnson Space Center is doing the observatory test facilities. The Marshall Space Flight Center is doing the mirror tech development and environment research. And the Glenn Research Center is doing cryogenic component development. So it's like spread all over NASA. It's not like within one center of NASA. And then we have the ESA, the European Space Agency, who's actually responsible for the instrument for the near infrared spectroscope, the mid infrared instrument optics assembly, and the launch vehicle itself, the Ariane. And then we have the Canadian Space Agency providing fine guidance, sensor, infrared image, and slitless spectrography. And then Northrop is the main contractor responsible for building the telescope, the spacecraft bus, the sun shield, and preparing for launch. And then we have the STS-CL, which manages the web once in its orbit. STS will take over and see the observations from a day-to-day basis. So that's a map of every organization in the US that has contributed to web in some way. So this is one of the videos. These are observations that you can expect from web once it's going into orbit. I'm not going to play this due to the time constraints in the presentation, but you can always check it out on the slides that we're going to share later. And these are just references to different things that we discussed in the presentation. So nothing much here. And you have online resources as well. So it's available in Facebook, all the social media networks, and then you have the specific websites that you can go to and learn more about the program. So plenty of online resources there to catch up as well. And we have a guest speaker who's going to explain the astrophysics part of it, and she will dive much more deeper than what I did today. So having said that, that's the end of my presentation.
Thanks, Kailash. Yeah, question. Christina, who's going to be talking to us in November, can you explain kind of exactly what she does, or do you know kind of her expertise in this whole project?
She is a doctor of astrophysics, and she works in NASA Ames Center here in Silicon Valley. So that's all I know about her, but I don't know specifically what she does for the Webb.
And I noticed on one of your slides, it was talking about the Hubble Space Telescope, which was had a mission life of like 28 years, and that this is going to have a mission life of 5 to 10 years. Do you know what the limitation is on this?
The limitation is the environment, basically. So once you go into deep space, you have to be concerned about radiation. You have to be concerned about several other cosmic waves hitting the interacting with the telescope more than the Hubble does. The Hubble is in the lower Earth orbit, so it experiences far less radiation, cosmic radiation. So that's one of the reasons why I think they've actually downgraded the lifetime of the Webb. It's basically, into deep space, you have more radiation to deal with.
Hi, question. Do you have a sense for how long it took to develop, and how much it cost to develop the telescope?
The schedule, I know that it's been slipping like for past 1.5 years or so. It's supposed to be launched somewhere in 2019, but now we are in December 2021. So it's a huge investment in terms of a project size, and the research itself began as early as 2016. So I'm not sure on the specific figures of the budgets, but the figures are quite astronomical, yes.
When do you think you'll get the first image after they launch?
So after they launch, after the telescope is parked in the L2 orbit, so they're going to do a series of dry runs in deployment, and then only then, like, it's going to take a month or two from that to make the first attempt in capturing an image. So it's going to be a slow process. So it's not going to happen in the next day or something like after deployment.
So did you say approximately 90 days?
Yeah, 90 days. Right? Yeah.
Thank you.
Question, considering that this have a lifespan of 5 years, is there already plans for something to supersede it?
Not at this point. We have never tried anything in this scale before. So putting something in L2 itself is a big challenge right now, because like it's going to take some time to get to L2 orbit. So we don't know what we have succeeding the Webb, but as of now, I don't have an answer to that.
Yeah, I was just wondering because, like Hubble, we've gotten a lot more out of it than we ever thought.
The other thing is Hubble
so
can.
The thing is, it kind of seems like there should be something else coming.
Yeah, there is a possibility that we can service Hubble because it's pretty much close to us. So we can, in the space shuttle era, maintenance was done regularly. Even now, I think using the Falcon system or some other launch vehicle, it is possible to get to the Hubble. So the point with Webb, though, is it's very difficult for a service team consisting of humans to reach L2. So L2 is like very, very far away. I mean, I'm not
expecting them to service it. I'm just thinking about
it's going to be a lot more, complex.
Richard West has a question.
Actually, it's from Squadron 80 in general. Major Abishan.
Oh, yeah, I asked if you know when they do get it operational, what its first images are going to be?
So we are going to one of the science goals of this project is to see the first objects in the universe that were formed after the Big Bang. So we are looking. Our primary target is going to be the galaxies that were formed right after the universe was established after the Big Bang.
Or and see what they see beyond current visibility ranges.
In the infrared range, basically you're going back in time to see how they look like and trying to derive answers on
Okay, so they don't have a specific target in mind.
No, not as of now, because they don't know what to expect in the first place, because they want to actually,
I got
actually see back in time, and they are trying to go back to the first galaxies that were formed after the Big Bang.
That's still not as far back as the cosmic background radiation, correct?
I didn't get your question, sir. Sorry.
The telescope, the Webb Telescope, is the further it looks, the greater the redshift. So its distance is limited by how low in frequency it can detect.
Yes, yes.
Okay, so it can't, for example, detect the cosmic background radiation map because that's down in the microwave region.
That's correct. That's correct. Yes.
Okay, so it's sort of it's looking further back than Hubble, but not as far as the radio telescopes that detected the cosmic background radiation.
I'm not sure about the radio telescopes because I'm not an expert in that. I don't know what exactly happens in a radio telescope, but all I can say is this is primarily more infrared, and we also have a visual component, but I don't think we have a radio component in there.
Right, thanks.
Yeah.
You said that the Lagrange point that this is going to be parked in orbit is 1.5 million kilometers.
Yeah, yeah.
And that translates to 92.4 million miles. That's not too far away from the sun. Isn't the sun 90? Cadets
we are going in the opposite direction from the sun, right? We are not going towards the sun. We are going the other way. So the idea is to actually get as far as possible from the sun. So we are
far away from the Earth as the sun is. The Earth is from the sun, but still,
the sun is
still need a cryogenics to cool that off.
Sir, the sun is 150 million kilometers, and this is 1.5. So it's 1% of the distance to the sun.
Correct. That is right. So the idea is to park this in an L2, or we chose L2 because we wanted very less interaction from the sun as well. So the Earth will come in between the sun at any point. Even then, you need protection from the sun. That's why you have all the telescope components that fold out and basically shield the sun's radiation. Whatever little comes from the sun. And the idea of choosing L2 is because the telescope would not experience any gravitational force from any object, because the gravitational pull or force is equal. There, the gravitation pull, the influence from Earth, the Moon, and then the Sun, they're all very, very much equal. So it's going to stay in the orbit, stay in that position for a while.
Sir, it appears the satellite is extremely complex. Is this probably the most complex spacecraft we will ever launch? Or
I can't say it's going to be the most complex, but this is how people at NASA and other space agencies are beginning to think. They're trying to put objects that are cramped and in a very small size, but it opens out into a very large object outside. So the technique comes from origami, which is a Japanese technique, basically folding things into smaller size. So if you have a sheet of paper, they fold it in such a way that it releases into that size later, but then it can be compressed into something initially for storage. So it's an art form that actually inspired people to think this way.
Thank you very much for giving this presentation. Very, very interesting.
Likewise, sir. Thank you. I hope you all enjoyed it.
Yeah, thanks a lot. It was good.
So
Thank
the
you.
odds are highly likely that the launch will be successful.
The launch is going to be successful. What's going to be more complex is the telescope unloading itself from its package. So that's the more challenging part. Everything has to go on by the algorithm that's created here. No one can go and perform a maintenance. That's the thing. As of now, at least, nobody is planning to go to L2 to actually fix something. So
Well, the
it's
odds
is
of
there-
it unfolding successfully are highly likely, or
highly likely, highly likely. They have rehearsed it so many times over here. It's not like they haven't. Yeah, I mean, we have achieved Mars mission successfully, so there's no reason why we should not be able to achieve this one. But the territory is we haven't done this before. This is the first time we are doing it. But origami is here to stay. Whatever we are doing in space, like origami is here to stay for the next missions for sure. It's a space architecture, and there's a lot of research going on in that front.
So do you work at Ames Research Center, or where do you work at?
No, I'm an engineer by profession, so I'm not I don't represent NASA in an employment capacity. So I'm just a volunteer and a NASA solar system ambassador. But my day job is I work with medical devices research and development. So more into design control of medical devices. Work with FDA, NASA. Yeah. But something which is very passionate to me is aerospace. So that's one of my reasons for joining CAP as well as representing NASA as a solar system ambassador.
Yes, Kailash is a minor celebrity. He's appeared on the BBC representing NASA on multiple different occasions. So definitely good there. Just a quick reminder from Major Obashan here that at Squadron 80 that he would like a copy of the presentation for.
Absolutely, sir.
Please.
Yeah, I'm going to send it to you and everyone. It's already okay. I mean, I should have shared it, Richard. You would have got it when I shared it to Mark, sir, before, but I can send it to you again.
I'll be sending it to everyone and we'll get a copy.
Yeah, sure.